Great. So, good morning again. I gotta boot up my tablet thing. 400 different buttons to hit before I can even start. Great. So, I wanted to remind people that I have some office hours hours 4 to 6 Eastern tonight. In case you have any questions about linear algebra stuff we've talked about that's not making sense, lecture today. Python, if you're having trouble installing Python or Pulp, might be a good time to ask me about that. This is the wrong zoom level. There we go. Yeah. So we're going to talk about, we're just going to do a few example problems today. I'm also going to throw you into some breakout rooms so you can chat amongst yourselves about some of these problems before I give you the answers and explain exactly how they work. We're also going to talk a little bit about mathematical programming as a sort of language, how we format things when we're presenting them, and what all information needs to be presented to a reader or a listener or whatever. So this is an example from the book, from the reading that was assigned for today. We have a water tech company. They are manufacturing things, some things, and each product requires some time on each machine and some level of labor from employees. And we want to produce things. We want to schedule production or pick how many things we want to produce from each product to maximize profit. And we can only have 700 hours on machine 1, 500 on machine 2, 600 hours of skilled, 650 of unskilled, etc. So this problem is in the book. We'll iterate on it later, but I just wanted to explain in words exactly how this model works. So the first thing we need to decide is what our variables are going to be. So we have a few decisions to make. We need to decide how much of product I to make and how much labor to hire. These are the things that we are asked explicitly to find out. Product I being a stand-in for 1, 2, 3, or 4 in this case. We're going to let xi represent that. That's just going to be a variable. And we're going to let ys and yu represent the hours of labor to hire. Then we need an objective function. Well, yeah. The problem wants us to maximize profit. So that's going to be maximize profit, which is, of course, sales minus costs, which is going to be the sum over I equals 1 to 4 of the sale price of I times x of I minus I think it was well, cost of labor times y. Jumped out of the wrong screen. Ditto yu. I think that's sort of what people are expecting. Is that unclear? No. Feel free to speak up or type in
Is
the
this
chat.
supposed to be? I mean, I read the text obviously, but I didn't see like this type of setup. But maybe I just missed over it.
I'm not sure this is exactly how uh, they described the problem, but this problem was in the book on, or at least
They just
it's
expressed it differently,
yeah,
that's all. I wrote down the formula that they gave us. It was just like a different writing of it.
right. And I'm about to give that um, um, their version of it here in a second. But yeah, that's example 1.1, first example. It's right there on page 2 of my copy. But so this reduces to 300 x1 plus 260 x2 plus 220 x3 plus yeah 180 x4 minus 8ys minus 6yu. They put some parentheses around this in the book. It doesn't really make a difference. It's just to show you things. It looks cleaner to me without it, but do whatever you want. So this is, of course, sales minus labor. So for every product they produce, we're assuming that they can sell everything that they actually produce. For every product 1, they make $300. For every product 4, they make $180. For every hour of skilled labor, they have to pay $8. So that's our objective for this problem. Yeah, okay. There's one more thing we need, and that's the constraints. The problem says that hours on machine 1 should be less than or equal to 700. There's only 700 hours available on the machine, so this is what our constraint's going to look like. Product 1 took 11 hours. Product 2 took 7 hours. Product 3 took 6. Product 4 took 5 hours. So that should be less than 700. Am I making sense here? Am I obfuscating something? Or is this good? Anyway, in a very similar vein, hours on machine 2 should be less than or equal to 500. And the hours of S, skilled labor, is less than or equal to 600. Hours of U, less than or equal to 650. And here's the maybe more interesting constraints. Hours of S used should be less than or equal to hours of S hired. This is the tricky constraint here. Everything else sort of makes it. I mean, it's obvious when you think about it. I need to hire as many hours of labor as I'm going to use, but it may not be obvious that that has a mathematical implication. So, and same for you, for the unskilled labor. So I'm just going to forgo writing all those constraints out here and write this in a sort of can I grab it? In sort of the format that we will be using for the whole class and that the whole OR sort of world uses. We're going to write our objective function first. So we want to maximize all these things. Well, this function subject to our constraints. So we're going to write our constraints out here, not an H. 11x1, 7x2, 6x3, 5x4, 700. So here's our constraint for hours hired of each one. Nope. The number of hours of skilled labor we hired has to be less than 600. And finally, did I skip ahead? No, we're good. 900 x1, no, not 800, just 8. So if we look back at what we had, product 1 took 8 hours of skilled labor, 2 took 5, 3 took 5, and 4 took 6. I just realized there were some questions in the chat. Yes. Thank you all for answering that question. Yep, I distributed the negative sign because there were parentheses here. I distributed that inside. Anyway, so those coefficients line up to this constraint, right? It took 8 skilled hours for each product 1, 5 skilled hours for each product 2, etc., etc. That all has to add up to be less than however much we hire of the skilled labor. Exactly the same idea for the unskilled labor. And there's one more formality that we need. So this in itself does correctly describe the problem that mathematically, right? There is one small issue in that we could feasibly have x sub 1 be less than 0. A negative number for any of these variables would be valid to these constraints. Now, because we're maximizing, it's unlikely that we end up with negative values for things. But as a formality, we always, always, always describe in our models the domain of every variable. In our case, any positive number or any non-negative number is fine. This is important. In this problem, it doesn't really play much of a part, but in many, many problems, if you forget to tell the computer that your variables should be strictly non-negative, you're going to run into issues. And so we always include this line here. So this is we're going to be looking at a lot of systems of formulations that look very similar to this. Our objective function, the sense that we want to optimize that objective function in, a list of constraints, and a non-negativity clause. Or in some cases, you might want negative variables. And you would list that down here at the bottom as well. So what makes up a mathematical program? I just went over that. What makes this one a linear program? Well, the simple answer is that every constraint and the objective function is linear. Now the book talks about affine functions and linear functions. In practice, in my experience, those two terms are used interchangeably. But it's good to have some exposure to both of those terms. So just briefly, a linear function is a constant times a variable plus however many more variables you want, plus a constant. This is the only form that our functions are going to take in this class. There may be some exceptions to that, but as a rule, these are the kinds of equations, the kinds of problems we're going to be learning how to solve. Things like x squared, x times y, root of x, log of x. We can't handle those with the tools that we're going to learn in this class. So a linear program is one where the objective is linear, the left-hand side of the constraint is linear, and the right-hand side is a constant. Now, we will do problems where we'll have a variable on the right-hand side, but the idea is that we could subtract that off and move it onto the left-hand side. We'll deal with that when we get there. So linear programs are what we're dealing with. Now let's change up that model a little bit. I'm going to quickly try to copy it. Where'd my cursor go? Copy our model here. So suppose that a union crops up in our water tech company, and they say you can only hire skilled labor in shifts of 5 hours. How does it change the problem? So previously we were thinking about labor as being this kind of fluid, hire exactly as much as you need to produce whatever. You could hire a quarter of an hour, you could hire pi of an hour if you wanted. This union is saying we can only hire chunks of 5 hours. How does this change things? Well, I think first we're going to redefine y of s. A triple line here just means it's defined this way. Number of shifts of s hired. Then we have to change a few things, right? If we're hiring shifts of 5 hours, then 5 times ys has to be less than 600, because there are still only 600 hours to go around. And in fact, a shift now costs 5 hours times the hourly rate. So 40 minus 40 ys. And there's another important part to this. Ys has to be in z. If you're not familiar with this symbol, z is the set of integers. Yeah. So the negative integers, the positive integers, anything you want. I, being a math major, really love this notation because it's simple and short. I believe the book simply says ys integer. Both are totally valid, and I will accept either one. But there are many ways to express some of these small little minutiae that some people care about. But it is important that we do express in some manner that ys has to take an integer value. Unfortunately, the scope of this class doesn't actually include much on solving integer problems with integer variables. We'll touch on the general idea of how it's done, but we won't go into depth. That's reserved for DOR2 and more specific application-based classes. So, moving on, if we grab our, let me do this with the, yeah. Mouse. Why did my mouse go over there? So let me grab this again. So now we have two types of shifts that we can use. Let's so we have 8-hour shifts and 5-hour shifts, and they come with different hourly rates. So I'm just going to express this as y sub s with 5 for 5 hours, y sub s with 8 for 8 hours. So stick with the 5ys5, but we also want to include 8ys8 in this constraint. And I deleted part of the objective function, but that's not a big deal. We still have plus 40ys5, but we're going to have a new 80ys8. Those should be minuses, I believe. Yep, because they're costs, not profits, not revenues. Minus, what was it, 6 yu. And further, we need to make sure that our new variables are, their domain is correctly expressed. Does everything I've just said here, have I made it clear? Is that,
Yes.
yeah, great, great. Is everyone understanding what the process is? Cool. So, if that's the case,
I have a quick
yeah,
question.
sure, yes.
Actually. Yeah. So it said wage of $10 an hour. What do you do with that 10? Like, I didn't see a change.
Sure, yes. So the wage would be $10 an hour times 8 hours is right here in that 80.
Okay.
All
right, yeah, that makes sense.
You do not necessarily, so everything I've been writing has been a single coefficient. You could write 10 times 8 times ys8 if you wanted to be, in fact, if you're presenting it to a company that you're contracting for, it may be more clear to write it like that, where we can say the hourly rate is contributing here and the shift length is contributing there. Some people might prefer that. Anything else? All right. Well, we're going to try something. I'm going to split you guys up into breakout rooms, and I'm going to give you 5 minutes or so just to think about this problem that I'm going to put up and write out a model, as much of a model as you can get in 5 minutes. And then I'm going to come back in and discuss my version. And I'll screen share the problem to the group. But first I'm just going to talk about it. So in the distant future, some spacefaring humans are on a spaceship. They eat Soylent brand NutriPaste. There's a few varieties of it, but one of the children on board, he has a sweet tooth, and he's developed a deliciousness index for each of the varieties that they have on board. And he wants to mix the different varieties to create the tastiest meal that satisfies his mom's requirements. At least 1,500 kilocalories, no more than 20 grams of fat, at least 100 grams of protein, and I thought I updated this page, but I guess I didn't. Exactly 30, not 300, cubic centimeters. and this should be tastiest or average tastiest. Formulate the problem as a linear program. Think about decision variables, objective function, and constraints. Yeah, so I'm going to throw some breakout rooms out there and then share this screen to all the breakout rooms. And you guys can have 5 minutes or so to think about that. Great. See y'all in a little bit. Oh, shit. Stop the share. Great. Was that fun at all? Was that break up the pace? I don't know. Think about that, and if you got any ideas, throw them in the feedback on the Google Forms, maybe.
I have a quick question.
Sure.
So, like, we were able to start like figuring out where to go. Um, I mean, firstly, didn't feel like the time was long enough, but that's besides the point. My question is, would you say that finding like the subject to lines would be like the easier way to start? Because I feel like that's what we struggled with was figuring out at the beginning
Where to start?
like where to start from, and then once we were able to do that, then it started to make sense.
Great. Good question. Good question. Um, well, let me take you through my thought process, and maybe that will help. So the first thing I want to do is determine exactly what decisions need to be made. So what are the variables going to be? Is sort of the mathematical way of saying that. What is the subject of the problem trying to decide? In this case, he wants to know how many cubic centimeters of each variety of soilant does he want to mix together? And maybe I didn't make that super clear in my problem statement. Um, so my variables look like this up here. So I had x sub b defined as the cubic centimeters of blue and red and yellow respectively. Did anyone have any trouble coming up with that? I'm not sure I made it.
I have a question.
Yeah.
Where is the 13 comes from? Honestly, I haven't saw the 13.
13? I think that's supposed to be a B. This 13, that's a B. Is that what you were asking?
No, no, no. I mean the max, the 0.1 over the 13. I haven't moved.
Oh, yeah, I'll get there. I see. So my first question is always, what are the variables going to be? What do my people want to know? And then you can either say, what's the objective, or what are the constraints? Yeah. So I usually start with an objective, but once you have the variables, you can do either one. So the objective was to create the average tastiest meal. So I interpreted that as the on average the highest deliciousness index, or maximize the deliciousness index of your mixture. So exactly 30 cc's means that the average deliciousness is going to be 1 over 30 times 0.1 x plus 0.25 xr plus 0.2 xy. And then I simply distributed the 30 inside those, or the 1 over 30 inside the parentheses. Is that answering your question?
Yes, yes. Thank you.
Great. And then I start working on the constraints. So the he needs 1,500 calories in the mixture, so the calories times the amount of each has to be greater than or equal to 1,500. The fats times the amount of each variety should be less than or equal to 20. And the proteins times the variety, the amount of each variety should be greater than or equal to 100. And then the total number, or the total amount of each variety should be exactly equal to 30. Now, when I first wrote this problem, I didn't include the 30 cc's exactly issue, and then I ran into a problem where the average was, instead of 1 over 30, it was 1 over xb plus xr plus xy times some stuff on the inside. The problem I realized is that this is not linear, so I was asking you guys to write a non-linear program. So I added this constraint so that the average would be a linear equation. So that's something to keep an eye out for if someone asks you to do an average that might not be linear. Anyway, we also need to have our non-negativity. Now this is a problem where the non-negativity could have a major influence. It could be that you can have, I'm not sure if this is really feasible, but it could be that you could crank up your amount of XB, which has a lot of deliciousness, and have a negative somewhere else to compensate for the amount of fat that's in XB. So here, our domain restriction is very important. Anyway, and there's a problem relating to this on your first assignment. So you may want to remember where this model is. So anyway, what if we change up, we have the same data, but the Starship is having some engine trouble. Well, actually, before I jump into this, does anyone have any other questions about this? I feel like maybe I went a little quickly. Did anyone have trouble coming up with something that looks a little bit like this? No? Alright. So, our spaceship has some engine trouble, and they're not going to make it to port quite as soon as they wanted to. So they're going to have to ration their supply of Soylent. At each meal time, 15 cc's of blue, 6 of red, 8 of yellow. The captain wants to maximize the calories in each meal without dropping the average deliciousness below 1.2. So given the same data and a different objective, we're going to have a whole different model, right? We want to maximize the number of calories. So you'll recognize this equation from our first constraint here that was on the number of calories. But instead of capping it or bounding it, we want to maximize that number. Such that, and our constraint now is that our deliciousness index is bounded instead of being our objective. And then we have a bound on the number or the amount of each variety that we can use. Here's how I like to write this constraint. Let me actually do a few different varieties here. X sub bar is greater than or equal to 0, but X sub bar is less than or equal to 6. That's an 8. All three of these mean essentially the same thing. That xb runs between 0 and 15 inclusively. So this is equivalent to a less than or equal to. You can also do 0 to 15 exclusively, which is a strict inequality. But we don't want strict inequalities here. This is maybe a more typical way to see it written out. But some people just throw that all into one line like this. All of those are valid. Do whatever you want. Do whatever makes the most sense to you. We got 20 and change minutes left. Let's move on to another problem, unless someone has a question here. No? All right. So the idea behind this was that with the same data, but a different objective, we might have a completely different model, formulation, whatever you want to call it. So let's think about this more abstract theoretical problem. Given an m by n matrix A and a vector B in Rm, if you're not familiar with this notation, this just means the size. Oh my. M vectors of real numbers such that AX equals B. You've seen problems like this in linear algebra, but let's assume that it doesn't actually have a feasible solution. Let's think about the problem of finding a vector in Rn which minimizes the deviation of that solution from our sort of system of equations here. Now, this is a bit of sloppy notation, but I want to use this absolute value component-wise. What that means is that expands out to that statement. There's a problem with this. This is not a simple thing to do. Why is absolute value not linear? Well, let's think about the plot of just. So if this is x, and this is absolute value of x, it's going to look something like that. That's not a line, that's two lines. So absolute value, in general, is not linear. And you have to make some moves to express absolute value in a linear program. So what we're going to do for each j in 1 to n, define xj plus to be the maximum of 0 and xj. Basically, we're taking the positive component of x. So if x is positive, it's going to be x. If x is negative, we're going to get 0. And very similarly, xj minus equals the minimum of xj and 0. Is that? Yes. So if xj is negative 3 is smaller than 0, we get negative 3 in the xj minus. So now we can break apart this absolute value, minimize sum I equals 1 to m, j equals 1 to n, aij xj plus minus aij xj minus bi, and that should be a parenthesis, not absolute value, such that xj plus is greater than 0, xj minus is less than or equal to 0. Both of these are for all j in 1 to n. So there's a few things to talk about here. Let's start with, is anyone not following my description of how this expansion of absolute value works? Let me write it on a slightly simpler problem. So absolute value of x is the same as x plus minus x minus. Let's think about that. Absolute value of negative 3 equals maximum of 0 and negative 3 should be 0 minus negative 3 equals 3. At the same time, positive 3 is going to equal 3 minus 0 and give 3. So what we've done is by altering the domain of our absolute value and restricting it and saying this domain is going to be one function and this domain is going to be another function, we have created two linear functions out of one that's not linear. Now, not everything, so I don't know how to do this with a logarithm, but absolute value you can do this with all day. Does anyone have any questions about that? All right, moving on. This notation, I haven't shown this off before, I don't think. This just says that these two constraints apply if I swap out the j for one of these indices between 1 and n. So the brackets, the curly brackets, indicate that this is a set and not an interval. So if I did 1 to n, that would be an interval. But a set just means we want all of the individual elements. So 1, 2, 3, 4, 5, 6, 7, 8, up to n. We don't care about the fractional parts. We just want the integers. Sometimes, I think the book, how does the book do it? The book says they do a parenthesis and they just say j equals 1 to n. If that makes more sense to you, by all means, use that. Once again, math major, I like my obscure math notation. Does anyone have any questions about that? We'll be doing this kind of thing plenty this term. Now, we're running a little bit short on time. Well, got 15 minutes left. Maybe not. But I had this planned as a group exercise, but we've already done one today, and I want to get to talking about how it actually works. So, we have a water company. It's preparing for the summer when water kind of dries up. Their aquifer stops producing quite as much. So they have to buy water from out of state. They have storage tanks on site that are capable of holding 100,000 gallons of water. Their monthly demand remains constant at 75,000 gallons, but their aquifer is producing less and less each month. We're going to let xi indicate the amount of water that can be purchased in month I. Where was I? End of month I. So SI, they can store some water in their holding tanks at the end of every month for use in the next month. Let's say there's already 30,000 gallons in storage for use in the first month, and we want to minimize cost of buying water from what the problem is in a linear program. We already have our variables, xi and si, so how much we buy and how much we store. So let's move on to the formulation. I need an extra page here. That's not the right one. Insert page. Great. All right. So minimize cost of buying water. So minimize the cost in month 1 was $1 per gallon. Month 2 is $1.25 per gallon, etc. Now every month we have some production. We have some that was left over in storage, or yeah, let's do it that way. Some production in month 1, plus what was stored from month 0, in this case, plus what the awkward, well, correction. We have what we buy from out of state as x1. S0 is the amount that's already in the holding tank in that month. We have how much the aquifer produces in that month. And we have how much we want to store at the end of that month. And all of those things have to add up to at least 75,000 gallons. Because that's how much their city needs to operate. This constraint has a lot of moving parts. So if you have any questions, feel free to speak up. And we replicate this. Oops. Replicate this for all 5 months. This should be x2. So we see here that we're subtracting from our production in month 1, and that carries over and is added to production in month 2. And same for month 2. We subtract some off, and we save it for next month. So that continues on. I think you get the idea of what that looks like. And then we were given that S0 equals 30. I think I have a slight magnitude error. 30,000. Also x1 or xi and si greater than or equal to 0 for all I in 1 to 5. So that's the whole model there, where there's a few more constraints that I didn't explicitly list out, but carbon copies of the ones above. So this is a pretty common sort of production planning trope within operations research, that we can store some of something and use it in a next period. I think the book had a nice example about multi-period planning, and maybe it was section 1.2 that was read. So I had one more example to talk about, but we only got 5 minutes. It's going to take longer than that. So I think, unless anyone has any questions that they want to call out or type in the chat, we can be done for today. This is our first real content day, so I would really appreciate any feedback. There's an anonymous form on the syllabus. If you think I'm going too fast, too slow, if you think me writing things out is too tedious, if you think you guys want more time to speak up in class, or if you want to do, I don't know, any suggestions would be excellent, because like I say, I'm new at this and I want to get good at it. And you guys know how you like to be taught. X3. That should be a 30, I think. if no one else has any questions, okay, are there any variables overlapping? If that makes sense. Should there be a distinct difference between the first set of S and the second? First set of S and the second. S1 is the same variable here and here. Same exact variable. And they're going to take a single quantity when we find a solution. So there's overlap in that both constraints have the same variable, if that's what you mean. And just the same, this S2 is the same as this S2, and this S3 is the same as the S3 that would show up going down. All right. I'll stick around for a few more minutes, answer any more questions, but you guys are free to go. Remember that there are some office hours 4 to 6 Eastern tonight. If you have questions and you can't make it, email me. Thank you all, everybody, for listening. Any feedback would be great.
I had a question about the office hours.
Sure.
So I have a class that goes from like 3:30 to 5. You said it was your office hours were going from 4 to 6.
Yes.
Okay, I just want to make sure.
I will be in the Zoom meeting that's linked in the syllabus, 4 to 6.
All right, have a good day.
You as well.
Hi, Professor. I have a question.
Sure.
I wasn't able to attend yesterday's class. I was wondering, just what you guys went through. Was it mainly syllabus, or did you guys cover any content?
It was mainly syllabus, and I did a few problems from linear algebra to refresh everyone on matrix manipulations, row operations, that sort of thing. And I did an example of some calculus optimization problems that that you guys should have seen in like calc, just to refresh everyone's memory on what the goal is, but no real content. No.
Okay, so no worries there then. Just
No.
take a look at the syllabus and practice a little more what we should know by now.
Yeah. So I did post a recording of the lecture on a YouTube playlist.
Okay.
If you
Perfect.
wanted to watch it.
Yeah.
It should be linked in the syllabus. It's linked in the announcement I sent out last night as well.
All right. Perfect. I'll watch that. Thank you.
Thank you. Have a good one. Great. Bye, YouTube.